All right, so continuing where we stopped last time, this is just the two more slides, part of section 10.1, the beginning of the chapter. And then to summarize, according to Arrhenius, acids are producing H plus, the hydrogen ion in water. Bases, on the other hand, produce the OH minus, the hydroxide ion in water. They are both good electrolytes, especially if they are strong acids and strong bases. And even if they are weak acids and weak bases, they do produce a smaller amount of ions. But the strong acids and strong bases are very strong electrolytes. Acids are sour, and then bases are, of course, bitter or chalky tasting. I don't recommend tasting um, any of the chemicals if you ever encounter them in a lab. Um, the acids, of course, you know that they're corrosive, they kind of sting. Acid burn, you are familiar with an acid burn. And then bases, on the other hand, are kind of feel very soapy or slippery, but they also do cause a lot of damage. So like when handling Drano, you're required to wear like heavy gloves to protect your hands. Um, they turn these uh, colored dyes like litmus and phenolphthalein different colors. So litmus is red in acid, it's blue in base. Phenolphthalein is colorless in acid and pink in base. And then, of course, they can neutralize each other. All right, so acids can neutralize base, and base can neutralize the acid. All right, so in the study check, it says match the formulas of acids and bases. All right, so this is the nitrite ion, NO2. So it's going to be the nitrous acid. This is, you have an OH, so it's a base. This is calcium, so calcium hydroxide. This is the sulfate ion, so sulfuric acid, okay? This is the iodate ion, so it is iodic acid. Okay, if it was HiO2, it would be iodous acid. And then this is a hydroxide and sodium, so sodium hydroxide. All right, section 11.2 is talking about the more expanded and the more relevant definition of acids and bases. This is the current definition of acids and bases, especially acids. In this kind of definition, you don't even require water. I mean, water can be present, but the presence of water is not even needed because the definition is different. An acid is a substance that is donating the proton or the hydrogen ion. All right. So this is the acid because you can see that the hydrogen ion is coming off this and going into the water, because on the other side you see the water with one extra H plus. Okay, so that's therefore it's H3O plus. And then what it once the hydrogen ion comes off, it leaves the Cl minus behind. All right, so the acid is donating its H plus, its proton. The water is grabbing or accepting the proton. All right, so water is the base because it's a proton acceptor. Now in Arrhenius definition, water would not be considered a base because there's no hydroxide that you can see in the water. All right, it doesn't produce hydroxide in water, doesn't produce hydroxide in water. All right, okay, so however, with the Bronsted and Lowry definition, water is able to act sometimes as a base by accepting a proton, or sometimes, if you look at the reverse, it's able to give up its proton. So it can even act as an acid, right, depending on what it's reacting with. All right. Now when that H plus comes and latches on to water, it latches on to the lone pair on oxygen, all right, creating what is called as a hydronium ion, okay? So it's this hydronium ion that is making the water acidic, okay? So it's the presence of hydronium ion that makes the water acidic. HCl is a very strong acid, therefore you don't see the double arrow, it's a single arrow. So you can forget that once you've added it to water, all you see in water is going to be the hydronium ion and the chloride ions floating around, all right? So HCl breaks up in water 100% dissociation. Now here you have ammonia. Now ammonia is actually pulling off a proton from the water, and therefore the product is an NH4 plus. What you then are left with once that H plus is pulled off is the OH minus. So indirectly the ammonia, by dissolving into the water, it's forming the OH minus, which is derived from the water, all right? So ammonia is grabbing a proton, so it's a proton acceptor, it's a base. The water is now behaving like an acid, all right? It's donating its proton, okay? So the end result is that you have a slightly basic solution. The double arrow indicates that it's more or less ammonia and water intact molecules. There's a very, very little amount of these ammonium and the hydroxide ion that form in solution. All right, so in the study check, it says in each of the following equations, identify the Bronsted-Lowry acid and base in the reaction. All right, so you can see here, this has to be the acid because the H plus comes off, latches onto water, because on the other side you see it's H3O plus and the H plus has come off, so therefore you're left with the nitrate ion. All right, so HNO3 nitric acid is the acid and water is the base. Here in HF, the H is coming off and then it's joining up with water to form H3O plus, and what's left behind is the F minus, the fluoride ion. So hydrogen fluoride is an acid. The water is again acting as a base. The double arrow indicates that it doesn't really break up as much as HNO3. HNO3 is strong, and therefore you see that single arrow. All you're left with once it dissolves in water is just the ions. But in HF, more of the HF remains unbroken. All right, so in this study check, it says identify each as a characteristic of an acid or a base. So sour means acid, producing OH minus, that's a base. Chalky would be base. Electrolyte, they both are electrolytes, produces H plus in aqueous solutions, that would be acid. Now, because of the way one is a proton donor, the acid is the proton donor, the base is the proton acceptor. Therefore, what happens is if you have a reaction which has a double arrow, as in the case of ammonia, it can go both ways. So in the reverse scenario, what happens is the A minus, all right, if this is the acid, the polyatomic ion or the anion now becomes the base, because it's able to get that proton off of this entity and become back the acid. All right, so the base now on the other side, it's become the acid number 2. So this is acid number 1, this is acid number 2, base 1 and base 2. All right. Okay. So acid 1 and base 1 are called as a conjugate base pair. Base 1 and acid 2 are another conjugate acid base pair. That means they're derived from each other. All right. So what they have in common is an anion. All right. As you can see here, what they have in common is an anion. Right. So it's a little bit more clearer here. You can see HF, right? That's the acid. Its conjugate base would be F minus, right? So the difference between the acid and its conjugate base is that the acid has one extra HF. Similarly, you have the base, which is water. And if you look at its conjugate acid, it has one H plus more, all right? So the acid part is always going to have an extra H plus compared to its conjugate base, all right? Or the base and its conjugate acid, the acid part will have one H plus more than the corresponding base, okay? So they have to be related by the loss and gain of H plus. Then they're called as conjugate acid base pairs. All right, so here, if you look at the reaction of ammonia and water, the ammonia grabs an H plus from water, so and becomes ammonium. All right, so NH3 NH4 plus are the conjugate base and acid pair, and then water is the base and its conjugate acid is H3O plus. Okay, this is the acid, F minus is its conjugate base. Okay, if this is the base, H3O plus is its conjugate acid. So it says here, write the conjugate base for each of the followings. Just remember the conjugate base lacks one H plus, all right? So take that off and you're left with a Br minus. Take one of the H plus off and you're left with an HS minus. Again, remove just one H plus off and what remains is HCO3 minus. Add an H plus to this. Okay, you're adding a positive. It already has a negative signs. They cancel, so it becomes HNO2. Add an H plus to this and it becomes NH4 plus. Add an H plus to this and it becomes H2O, water. H plus and OH minus are basically water, H2O. So it says here, identify the sets that contain acid-base conjugate pairs, all right? All right, they have to be related, all right? So you see here, what they have in common is the polyatomic ion, the nitrite ion, all right? NO2, NO2 minus, HNO2, and NO2 minus. So this is a conjugate acid-base pair. This is the acid, this is its conjugate base, all right? Now these two, even though they seemingly seem related, it's incorrect, because if this is the acid, its conjugate base should have been HCO3 negative, all right? There only one H plus should have come off, leaving the other H behind, and then the whole thing would have one negative charge, so HCO3 minus, all right? Now these are unrelated. This is the chlorate, perchlorate ion. This is HCl, hydrogen chloride. These two are related, all right? So you have H2S, that's the acid. The H plus part comes off, and what you're left with is the HS minus its conjugate base. This is the base, and this is its conjugate acid. All right, we'll stop here and continue this in the next slide, in the next video, sorry.